The James Webb Space Telescope, JWST, marks an important moment in the history of the universe, ushering in a new era of discoveries that could revolutionize our understanding of the universe. The journey to this important moment is long and full of challenges. JWST is intended to be the successor to the Hubble Space Telescope, which has been a cornerstone of astronomical exploration since its launch in 1990. Hubble gave humans unprecedented views of the universe, revealing galaxies' distances, star formation regions and more. But despite Hubble's power, it has limitations, particularly its ability to detect the first universe. The JWST was designed to overcome these limitations, offering a much larger mirror, advanced infrared capabilities, and a position far beyond Earth's atmosphere to provide clearer and more detailed images of the cosmos. The development of the JWST was a monumental task that spanned decades, involving collaboration among NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The project faced numerous technical and financial challenges, leading to delays and cost overruns. Originally scheduled for launch in 2007, the JWST's launch was postponed multiple times, finally occurring on December 25, 2021. The delays were partly due to the need for cutting-edge technologies that had never been used in space before, such as the telescope's large segmented mirror and its sun shield, which had to be folded to fit into the launch vehicle and then deployed in space. These innovations were essential for the JWST to achieve its mission goals, which include studying the formation of stars and galaxies, observing the atmospheres of exoplanets, and peering back in time to see the universe as it was just a few 100 million years after the Big Bang. One of the most exciting aspects of the JWST is its ability to observe the universe in infrared light. Infrared observations are crucial for studying the early universe because light from distant objects is redshifted due to the expansion of the universe, shifting it into the infrared part of the spectrum by the time it reaches us. Hubble, while capable of some infrared observations, was primarily designed to observe invisible and ultraviolet light. The JWST's infrared capabilities allow it to see through dust clouds that obscure visible light, revealing the processes of star formation and the structure of galaxies in unprecedented detail. This ability is important for understanding the early stages of galaxy formation, as early galaxies were obscured by dust that could not be seen by telescopes like Hubble. JWST's position in space is another important factor in its ability to change our understanding of the universe. Unlike Hubble, which orbits the Earth, JWST is at the second Lagrange point, L2, about 1.5 million kilometers from Earth. This position has many advantages. First, the telescope remains fixed on the Earth and the Sun, so that the view is not interrupted. Second, the lens hood can block heat and light from the Sun, Earth, and Moon, keeping the telescope at the very cool temperature required for infrared observations. This stable, cold environment is important for JWST to detect faint infrared signals from distant galaxies and other celestial bodies. Based on its advanced capabilities, JWST is intended to confirm and expand upon theories developed based on observations by Hubble and other telescopes. One of the main goals is to study the reionization period, a time in the early universe when the first stars and galaxies formed and ionized the surrounding hydrogen gas. This was the end of the dark ages of the universe, when stars were not formed and the universe was filled with hydrogen-free gas. By observing galaxies from this period, the JWST was expected to shed light on how the first stars formed and how they influenced the evolution of the universe. However, the early observations from the JWST have surprised scientists by revealing a universe that is more complex and structured than previously thought. The telescope has detected a large number of galaxies from the early universe that are much older and more mature than expected. These galaxies, such as Glass Z13 and Maisie's galaxy, challenge the traditional understanding of galaxy formation, which posits that galaxies evolve slowly over billions of years through the process of merging and accreting gas. The discovery of such well-structured galaxies in the early universe suggests that galaxy formation may have occurred much more rapidly than previously thought, or that the mechanisms driving galaxy formation are more complex than the current models can explain. This discovery has major implications for our understanding of the Big Bang theory, which has been the most important model for explaining the origin and evolution of the universe for nearly a century. The Big Bang theory states that the universe began from a very hot, dense point known as the singularity, and that the universe has been expanding ever since. According to this model, the early universe was a chaotic place, and galaxies would have slowed down over time as matter cooled and merged. The discovery of older galaxies in the early universe challenges this view, suggesting that the universe may have been more stable and ordered much earlier than previously thought. Based on these findings, some researchers are also examining other theories of the universe that have been proposed over the years. One such theory is the steady-state model, which posits that the universe is eternal and unchanging, with new matter continuously created to maintain a constant density as the universe expands. Although this theory fell out of favor in the mid-20th century with the discovery of the cosmic microwave background radiation, CMB, a remnant of the Big Bang, the JWST's observations have reignited interest in alternative cosmological models. If the universe was indeed more stable and structured in its early stages than the Big Bang theory suggests, it could imply that the CMB is not a remnant of the Big Bang, but rather evidence of a different process altogether. Another alternative theory that has gained attention in light of the JWST's discoveries is the cyclical universe model, proposed by Sir Roger Penrose. This model suggests that the universe undergoes a series of cycles, each beginning with a Big Bang and ending with a Big Crunch, where the universe collapses back into a singularity before starting anew. According to this theory, the Big Bang that we see is not the actual beginning of the universe, but only the last in a series of such phenomena. The circular universe model allows some structures from the previous universe to survive into the next cycle, which may explain the presence of mature galaxies in the first universe observed by JWST. The JWST observations raised questions about the nature of the universe's expansion. The traditional model of the universe's expansion, based on observations of distant galaxies moving away from us, suggests that the universe has been expanding since the Big Bang. The expansion is attributed to dark energy, a mysterious force that makes up 68% of the universe and accelerates the expansion. However, the discovery of ancient galaxies, formed in the early universe, may show that the expansion of the universe is not as simple as previously thought. If the universe was more stable and less dynamic in the beginning, it might indicate that our current expansion was not the result of a single explosion, but a complex process that is still not fully understood. The results of these discoveries will go beyond the universe and answer fundamental questions about the nature of space, time and matter. If the universe is older and more complex than the Big Bang theory suggests, then our understanding of modern physics may be wrong. JWST's observations will force scientists to rethink basic principles of physics, especially those related to the early universe. For example, the discovery of mature galaxies in the early universe could imply that the processes of star formation and galaxy evolution are more efficient than previously thought, or that new physical laws are needed to explain the rapid development of these structures. As scientists work to incorporate the JWST's findings into existing cosmological models, they face the challenge of reconciling the new data with established theories. This process is a fundamental aspect of the scientific method, where new evidence leads to the refinement or replacement of existing theories. In the case of the JWST, the challenge is particularly daunting because the telescope's observations seem to contradict many of the assumptions underlying the Big Bang theory. However, this contradiction is also an opportunity for scientific progress, as it may lead to the development of new theories that better explain the nature of the universe. The result of this process is the development of a new model of the universe that includes elements of the Big Bang theory and some theoretical models. For example, some scientists have suggested that the universe has several phases of expansion and contraction, each phase corresponding to a different time in the galaxy's formation. This model can explain the existence of older galaxies in the early universe by assuming that these galaxies formed in the early expansion phase, before the time of the expansion of the universe. That model represents a major departure from the traditional worldview, but it can provide a more accurate and comprehensive explanation of JWST's observations. Another area of research that will benefit from the JWST observations is the study of dark matter and dark energy. These mysterious substances make up most of the mass and energy of the universe, but their nature is still unknown. JWST's observations of early galaxies provide new clues about the role of dark matter and dark energy in the formation and evolution of cosmic structures. For example, the presence of highly formed galaxies in the early universe may indicate that dark matter played a stronger role in galaxy formation than previously thought, perhaps by acting as a scaffold so that common substances can be combined.